Okay, so I told the rest of the class, we went through a couple examples, and then there was a whole bunch of multiple choice type problems in the packet that they were responsible for that could possibly show up in your future test. So make sure that you go through those. So let's get into electric forces. Just a quick refresher, this value right here will definitely be on your equation sheet. If you look on your AP equation sheet, there's all these different constants and stuff. So make sure you keep this little guy handy that your fundamental charge is 1.6 times 10 to the negative 19 coulombs. Everything is measured in coulombs for us now for the SI unit for charge. I don't know what they measure in chem, but for us for charge it's coulombs. Okay, so that's where we're heading. Make sure you guys keep this little guy in your back pocket as well, because you may need that as we go. All right, so here's our new equation. Okay, and if you look at your AP equation, you can go check. I went to the electricity section, and now I have a new equation. Now, what does this mean? All right, if you have, for example, something that's charged up. Okay, so let's say that this charge over here, we're going to call it 2Q. All right, so it's 2 times the charge of, let's say, this negative charge over here. So he's Q. All right, and there's a certain distance that these guys are separated. And just like gravitational, okay, so for a brief moment, what I want you to do is pull out your AP equation sheet, and I want you to tell me the equation for gravitational force. Go ahead. So you said, what now? What is it called? What is it?
Big G.
Big G? Okay? Now, keep this in mind. So this is your gravitational equation, right? Well, for our electric force, all right, F little E, all right, it's going to be equal to, it says Q1 times Q2, all right, times your K. We're going to talk about K, right? Just like big G is a constant, K is going to have a special value as well. So within this example, if I was looking at this guy, these guys are super attracted to each other, right? So this guy's attracted to this, and he's attracted to him. Now, the way that you write this, all right, the way that you write this, notice it says 1 on Q, 2 on 1. And the reason they put this in absolute value, please note, okay, this thing is not an absolute value when we solve for it. The reason they're showing you these charges in absolute value, because they're just trying to explain to you that these are equal but opposite. Okay? So what happens here, if we write this electric force, and let's say this guy right here, if you were to write him, and if you want to call him 1, we'll call him Q, because it might be a little easier to write it, then this force right here that's coming off of him, right, is coming, isn't this force actually on him? Do you guys see that? And this force is actually on him. So this force right here, you would say that it's actually 1 on Q. The last number is the on, whoever you're on. So this force right here is attractive, and it comes over here, so it's always 1 on Q. If it's 2 on 1, then it's actually located on the charge 1. Does that make sense? That's how to write it. But if we were to look at this, it doesn't matter which one we look at, okay, because the equations are still going to be the same. The only thing that you have to, the equation itself will be the same. The only thing that you have to think about is this whole 1 on 2 or 2 on 1 is determining, okay, are you trying to find the force on this charge, or are you trying to find the force on this charge, right? That's all you're trying to figure out, because eventually we're going to sum forces, because when we have more than 2 charges, we got to find the net force, right? Okay? So, what happens here then, you would just multiply this to be Q, you get negative Q, times the 2Q, right, divided by R squared. Okay, and that would be your equation. If your Coulomb, if your Q is strictly 1 times 10 to the negative, what was it I told you to keep the value of?
1.6 times 10 to the negative.
Yeah, if each Q is that, then you would just multiply these Q's across, and your electric force would be negative, depending on which direction. It would be negative if you're looking at this force going on this guy. Do you guys see that? But if the force is going this way, it's positive. Do you guys see that? Okay? So when they put absolute value here, the reason they do that, one way to think about that is if you don't put the negatives and positive into the equation, which you don't have to, you do need to look at the end to say, whose force am I looking at? Okay? Because if you're saying, okay, Q is emitting a charge to QQ, agreed? And if you're looking at the force applied on him, it's in that direction, so it's negative. If it's this force on him and it's going this way, the force is positive. Right? They're equal but opposite, but one's going to be negative, one's going to be positive. Okay? Yes?
Did you need like the electrostatic constant
got a mean cube?
The K right there.
Oh, I forgot about the K. Sorry. Yeah. Okay. Thank you. Yeah. Thank you. Yes.
Will they have to give us the Q value?
Yeah, I'm just theorizing. We're gonna talk about Q here in a second. Okay. If they give you, if it is Q, like a lot of times what they'll say is like it's 2 times 10 to the negative 9. Like 2 microcoulombs or 2 nanocoulombs is usually pretty common. It's usually in micros and nanos. And we'll go through an example here in a second. But know that if they just say Q, that means, or if they say if it's the fundamental charge, right, which is E, then that's your charge. If they say it's a proton, you're going to go with the proton. If they say it's electron, you're going to go with your proton. And all of your E's and your Q's and your proton charges, all that is on your AP equation sheet. Okay? Now, go to your AP equation sheet and go look at K. Okay, so if you're looking at this guy, you may find it. No, not even close. It's 1 over 4 pi, and it has this little e. Okay? And then it comes out to be 9.0 times 10 to the 9th. This is really long. And of course, there's a, yes, is there a value for this little e thing? Yeah, but they don't seem that they care.
It is Pi Day. Hey, today is. It is. Ooh. You good, girl? Happy Friday, everybody.
It is Pi Day. Okay. And I have been thinking about banana pudding, but I knew the seniors were here today, and we're going to do it for you and Dealey's birthday, so.
I'll text you tonight.
We'll do it Wednesday when you guys have the lab. Okay, so this is your K, all right? Ladies, this is your K, all right? And you can go use it, and you'll go use that in your equation. Now, you should notice that these equations are very similar, right? Your electric force and your gravitational force are very similar. The difference, though, with gravitational, it will always be attractive force. It's a non-contact force, and it's always attractive. Electric, okay, electric force is a non-contact force, but it can be positive or negative. It can be attractive or repulsive. Repel, right? It can be both. Gravitational never repels. It always attracts. Does that make sense?
Yes.
Okay, so this kind of goes through and shows you what I was talking about. You got 2 positive charges here. They will repel each other, right? So this force right here, notice that it's called Q1. This is your Q1. But they say the force 2 on 1, right? So this force that's coming off of him is because he's repelling against that positive charge up there. So it's on the 1, but it's due to the force on charge 2. Does that make sense? And then vice versa here. All right, so just make sure you get familiar with the terminology stuff. Actually, doing electric forces will help you with gravitational. I know you guys weren't a big fan of it, but it will help you a lot. So.
Free fall.
Okay, you guys can kind of blow through this. The only thing that I want you to realize is that the word force and vector is still the same. We still apply forces. We still sum forces. We still find net forces. There's still a vector. So that means that if you have a force that on something that goes that way on a charge, and a force that goes that way, right, this is F1 and F2, you still get to sum them, right? It's just like drawing a free body diagram. Now you're drawing a free body diagram on a charge, okay? And so that means that, let's say this value is 10, and this one's 20. Because he's negative, your net force would just be 10 minus 20, and you would have a net force of 10 newtons, I don't know why I said charge, acting on that little point charge, whatever it is, right, due to all the, whatever is around it. Okay, so the rules still apply for net forces. That also means, though, which we'll get into, is when you start having a charge here and a charge here. And he's like 1, and he's 2, and he's 3. And what we want to understand is what happens to this. These 2 charges, when it applies a force on this guy, where's he going to go? Okay, so that's called a 3-point charge or a 4-point charge. And you'll have to understand and some of the forces on that, and we'll use a little bit of trick, right? So forces don't go away. The same concepts are still there. It still sums, right? Just like anything else. Okay? Okay, so let's talk about some concepts, and then this afternoon we'll do some math. All right, so if you're looking at this, does that mean?
Say goodbye.
She loves you.
Um,
Bye.